All right, guys, so what we're going to be talking about today is one of many different applications that we have for the derivative. If you've had, especially like AP physics or even basic physics, a lot of the things we're going to talk about here are going to seem at least somewhat familiar to you, but we are going to be looking at them from a slightly different perspective, like a mathematical perspective. So just kind of keep that in mind, okay? Now, we've talked about the derivative as a formula to help us find the slope of the tangent line. And that is great when we're looking at things mathematically, and it seems like that's not even that big of a deal. Like, why would we care what the slope of the tangent line is? And quite honestly, in a lot of ways, it's not that big of a deal that you can find the slope of the tangent line just by itself. Like, that slope just by itself without any other context would not be that big of a deal. But in reality, what happens is if we find the derivative of something that is happening at a given instant, what we're doing is we're saying, okay, that is telling us how fast something is changing. And so another name for the derivative is, it is actually the instantaneous rate of change. And so the instantaneous rate of change, it might not seem like it's that big of a deal, but when we take it and realize that what we're talking about is a rate of change, all of a sudden this becomes a much bigger deal for what we're looking at. Specifically, as we look at an object that is in motion. So let's say we had, then you can kind of see it over in the corner, hopefully. If not, let me move this screen up into the corner. No, move it down here. Oh, pretty good. Now I'm just gone. Great. Okay. So anyway, as we look at this, we've got this rock down in the corner. Now, if we were to watch the rock kind of do something like, oh, come on, why is it not moving? Okay. So if I were to watch this rock goes up in the air, and I apologize if this comes out loud on, hopefully it's not too loud on your screen. So that rock goes up in the air, and then it comes back down. Now you might be saying, okay, big freaking deal. Well, in the world of physics and in the world of calculus, there are many things that we can do when we talk about objects that are just moving in one direction, like forwards and backwards or up and down. And one of the things that we can do is we can write an equation like we see right here. We've got S equals 128t minus 16t squared. That equation might not seem like a big deal, but what that is actually is an equation that will allow you to tell where the rock is up in the air relative to how far he was off the ground at any given time. Where in this case, that is measured, like the position is measured in feet, and the time is measured in seconds. So I've got this S, and I don't know why they decided to use S to represent time, or represent position, but they did. It doesn't stand for speed. It doesn't stand for anything else like that. It stands for position. And so anytime you see S in a calculus class, what you are looking at, it might be S of t, but what you're looking at is a position equation, which again is just an equation that represents how high this rock will be at any given time, and it is accurate. Like, if this were really launched in the air with an initial velocity of 128 feet per second, this equation would tell us exactly where the rock is at any given time. And all we would have to do is take that time in seconds and plug it into the equation, and it would tell me exactly how high the rock is. Okay? So again, we use S. So here it goes, launching up in the air, same thing. And this equation will tell us at any given time how high the rock is in the air. So if I had an equation like this one, and I wanted to know, and so if I wanted to, oh gosh dang it, sorry. So if I wanted to know how high off the ground the rock would be at 2 seconds, I would just take 128 and plug 2 in, and it turns out at time equals 2 seconds, I would be 64 feet above the ground, because I just plugged 2 in for t. If I wanted to know at what times the rock would be 256 feet above the ground, all I would do is I would take 256, and notice I put that in for S, which denotes position. And we would solve that, and that's not something we're going to have to do on the AP test, so that's not what we're going to do here. Now, if we were to take the derivative of this position function that we're talking about with respect to time, in other words, I just want to find ds dt, what that gives us is it gives us, again, I said it's ds dt, but what it gives us is a very small change in distance divided by a small change in time. And before, we said if we have a distance traveled and we divide that by the time elapsed, that gave us average velocity. And we've talked about that before. That's what you've always defined time as. So a small change in any change in time, distance divided by any change in time, would give us our average velocity. But in this case, because these changes in time and changes in position are very, 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 very small, like they're just a split second, like bam, bam is your change in time. And your change in position is very, very, very small. So small, in fact, that instead of having an average velocity like we had before, this turns into an instantaneous velocity. And so the derivative is just from here on out, anytime we have the derivative of position, we will call that velocity. And if we're actually asking for average velocity, you will see the word average come with it. So if I wanted to know how fast the rock was traveling, if I were to find my derivative, okay, and you can see here the derivative has been found, 128 minus 32t. We just took the derivative of 128t minus 16t squared. When we take the derivative of that, we get 128 minus 32t. And that, notice we use the symbol v to denote velocity instead of ds dt. So I would take 128 minus 32 times 1.4, and if I put that into my calculator, then what I get is 94.6. If I do that right here, so I get 94.6. Now again, that might not seem like a really big deal, but what we have just found is that would be measured in feet per second. But what we have just found is a formula that allows us to tell how fast we're going at any given time, and it does it really quickly. Like I just had to plug 1.4 into this equation, and it told us how fast the rock was traveling at that time. The fact that we get 94.6 feet per second is a big deal. And that's just 1.4 seconds after the rock was launched up into the air. Now, a better question might be, how could we figure out when the rock reaches its highest point? Now, if we think about it again, the rock goes up and it comes back down. So that might almost be like if we were to look at that, that might be kind of like a function that tells us how high the rock is at any given time. At the very top right here, let's think about that for a second. The slope of the tangent line at that point would be 0. And so what I could say is its velocity at that time, because it's how fast it's going, which is the derivative of position, would be 0. So for a split second, when the rock gets to its very highest point, it's neither going up nor going down. It has no speed whatsoever. So I could say that its velocity at its very highest point is 0. Then I would just go about solving this equation. So I would get that t is equal to, in this case, 4. So at time equals 4, that's when the rock reaches its highest point. Furthermore, if I wanted to know what the highest point was, what we'd have to realize is, well, that's asking us for a position. So I wouldn't use my velocity equation. Instead, I would go back and I would use my position equation, which was 128t minus 16t squared. And if I wanted to know the position at that time, I would just take 4 and I would plug that in. And when I do that, what I get is, I'll put this into the calculator real fast, 128 times 4 minus 16 times 4 squared gives us 256. So we know that the highest the rock got was 256 feet up in the air. So again, our velocity can help us find the time when that happens. Then we can go back and plug it into our position to find out what that highest point was. Now, we have to be careful on a question like this, because notice it's asking, at what time did the rock achieve a speed of 64 feet per second? There is a small difference between speed and acceleration. When you think about it again, the rock goes up and it's going to come back down. And we found already at time, or what we could say is, all right, my velocity is equal to 128 minus 32t. So if I wanted to know when the rock is going 64 feet per second, I could just put 64 into my velocity, because that's what it tells me is how fast it's going. And I solve here, and I would find out, just like kind of we were talking about before, that at time equals 2, we know that the rock is going 64 feet per second. But there is a difference between velocity and speed. And it's a small difference. It's a subtle difference, but there is a difference. The difference between them is speed just tells you how fast you are going. Velocity tells you how fast you are going and the direction in which you are headed. So if I want to know when the speed is 64 feet per second, there's going to be a time when the rock is going up that it hits that speed, and a time when the rock is going down that it hits that speed as well. The way that we would find that is we would say, okay, it's going 64 feet per second, but if I have a negative velocity, sorry, there's a brief interruption there. So what we have to say is if the velocity is negative, then it just means the rock is going down. So if I had a velocity of negative 64 feet per second, all that means is I'm going 64 feet per second in a downward direction. So I would set this equal to negative 64, and I would get negative, if I were to add these together, 192 is equal to negative 32t, which would mean at time equals 4, by dividing both sides by negative 32, at time equals 4, or excuse me, 6, not 4, I apologize, 6, bad math. Time equals 6, I would have a second time where the rock is going 64 feet per second. And so another way that we could say that, what we were just talking about, is that speed is equal to the absolute value of velocity. Again, speed is just velocity without direction. When you say you're going 55 miles per hour in your car, or 88, or 112, or however fast it is you're driving, you have to understand that you're really always talking about a speed. It's never a velocity. If you said I was going negative 55 miles per hour, that would probably mean that you are coming home, but nobody says that. So you're always talking about a speed when you're driving a car. In reality, a velocity has a direction associated with it. Now, if we were to take the derivative of the velocity, we would get a small change in the velocity or over time, or we would like to call that the acceleration. So when I take the derivative of the velocity or the second derivative of position, we get a formula that tells us how fast we are accelerating at any given time. So the actual definition is either, if we're talking about the units that are associated with it, it would be like feet per second squared. And I know that doesn't make a ton of sense, but just kind of roll with me on that one. Those are the units that are associated with it. And it does make sense. I just don't want to take the time to talk about it. I'm not going to lie. Okay? Another way that we look at it that I think makes more sense is rather than looking at the units, it is a force that causes something to speed up or slow down. One example of an acceleration that you're familiar with is gravity. Gravity is this thing that causes you to, when you jump in the air, it's what causes you to speed up or slow down until you start coming towards the ground, and then it causes you to speed up. And we'll look more into this idea the next time when we come to class again next time. Okay? So in this case, if I had my position equation, same one. If I have my position equation of 128t minus 16t squared, and I wanted to find my acceleration, I would first find my velocity, and then I would find my acceleration is negative 32. And so what we would have to do is we would have to say, okay, it's negative 32. What does that mean? Well, what that means is the acceleration is always negative 32, which makes sense because gravity is a constant, and in our example, that was the acceleration that was acting upon the rock. Okay? So, as a quick recap for what we've been talking about thus far, if I have the position equation and I take the derivative, that gives me the velocity equation. If I take the derivative of that, then it gives me the acceleration, and all of those are different formulas to find out those things at different times. And then the last thing we have to talk about that we learned about today is that speed is equal to the absolute value of velocity. Now that was a decent amount of stuff, and again, if you've had physics, most of that should have sounded at least vaguely familiar. We've kind of tied it in mathematically. We will continue to talk about this in our next class, but if you have any questions about this, please come on in and I will answer any questions that you have.